Let us look at another problem related to eigenvalues and eigenvectors. We have a transformation matrix A equal to this. We have to find the special vectors whose direction remains unchanged under the transformation represented by A and find the corresponding scaling factors. Now, remember, determinant of A minus lambda I equal to 0. Lambda I is going to be everywhere 0 except in the diagonal. We will have lambdas. So 6 minus lambda, 3 minus lambda, and 3 minus lambda. Now we reduce this determinant. So apply determinant preserving row column operations to simplify the determinant. So we start reducing it. So when we replace R1 with R1 plus R2 minus R3, we get 2 minus lambda, 2 minus lambda, 2 minus lambda in the first row. So we factor it out. We get 2 minus lambda, the determinant equal to 0. Now we carry out some column operations. C1 replaced with C1 plus C3, C2 replaced with C2 plus C3. And we get this determinant equal to 0 times the 2 minus lambda. Another thing to notice is that the second column, 2 minus lambda, 2 minus lambda. So we factor out 2 minus lambda from second column. What do we get? Now we get 2 minus lambda square times the determinant of 0, 0, minus 1, minus 3, 1, minus 1, 5 minus lambda, 1, 3 minus lambda. And now we actually evaluate the determinant. So 2 minus lambda square times minus 1 times minus 3 times 1 minus 1 times 5 minus lambda equal to 0. Now simplify to get 2 minus lambda square times 8 minus lambda equal to 0. So which means 2 minus lambda square equal to 0 or 8 minus lambda equal to 0. So that means lambda is equal to 2, 2 and 8. Here 2 is repeated. So eigenvalues are 2, 2 and 8. Now we find the eigenvectors. We have already found eigenvalues are 2, 2 and 8. Case 1. Let's take lambda equal to 2. Substitute the value of lambda in this determinant. 6 minus 2, 4. 3 minus 2, 1. 3 minus 2, 1. So we have for case 1, this transformation matrix times the components of the vector equal to 0. Now we reduce the transformation matrix. Replace R2 with R2 plus R3. Replace R3 with R3 minus R1 by 2. We get 4 minus 2, 2, and the second and third rows are zeros. Now let's simplify it. Again, by dividing R1 by 2. We get 2 minus 1, 1, and the rest are zeros. Which means, by looking at this itself, we know that the rank of this transformation matrix is 1. And which basically also tells us that there are 2 free variables. So now let's convert it into equation forms. We get 2x1 minus x2 plus x3 equal to 0. x1 is equal to x2 minus x3 by 2. Second and third rows are zeros, right? So which means x2 and x3 are free variables. So let x2 equal to k1, x3 equal to k2. Then our vector becomes in general form k1 minus k2 by 2, k1, k2. Let's substitute some values. Let's say k1 equal to 1 and k2 equal to 0. We get this vector half 1 0. Now let's take k1 as 0 and k2 as 1. So our vector is minus half, 1, 0. These are the two vectors linearly independent and form a basis for the eigenspace corresponding to lambda equal to 2. So here we have one basis vector, we have the second basis vector corresponding to lambda equal to 2. Now let's look at lambda equal to 8. So when lambda equal to 8 and we substitute it into the determinant, we get 6 minus 8 minus 2, 3 minus 8 is minus 5, minus 5. And we repeat the same process here again. Start reducing it by carrying out the appropriate row and column operations. Column operations here, of course, not required at all. By looking at this matrix itself, we know that the rank is 2 and there is one single free variable. Converting it into equation form, we get minus x1 minus x2 plus x3 equal to 0, which can be written as x1 equal to x3 minus x2. Then we have minus 3x2 minus 3x3 equal to 0, which means x2 equal to minus x3. Now, since there is one free variable and that is going to be x3, let x3 equal to k, which means x2 will be equal to minus k and x1 will be k minus k, that is k plus k, which is 2k. So our eigenvector in general form will be 2k minus k, k. The eigenvector corresponding to k equal to 1 will be 2 minus 1, 1. We have found the eigenvectors. Eigenvalues are 2, 2 and 8. So basis eigenvectors are 1 by 2, 1, 0, minus 1 by 2, 1, 0, and 2 minus 1, 1. How does this look in graphical form? We have this. So here we have, now the green one is minus half, 1, 0. Red one is half, 1, 0. And this purple is 2 minus 1, 1. Now we have these three basis eigenvectors. When it comes to lambda equal to 2, we have got two eigenvectors. That means its eigenspace would be, when lambda equal to 2, it will be the all possible linear combinations of these two vectors, which we call it as span. So the eigenspace for lambda equal to 2 is the span of these two basis vectors. And the span of these two basis vectors would be this plane. Similarly, eigenspace for lambda equal to 8 is the span of this vector, which will be a straight line passing through the origin. Now, we have seen that an eigenvalue may repeat as a root of the characteristic equation. This repetition is called algebraic multiplicity. For a given eigenvalue lambda, the set of all solutions of a minus lambda I times x equal to 0 together with 0 vector forms the eigenspace. Remember, the eigenvectors themselves are non-zero vectors. So we have to explicitly include 0 vector, mainly because this is a homogeneous system and 0 vector would be a trivial solution, which is a solution for all homogeneous systems. If A is an n by n matrix, then n minus the rank of A minus lambda I gives the number of free variables in the solution of A minus lambda I times x equal to 0. This determines the dimension of the eigenspace, called the geometric multiplicity. Geometric multiplicity is always less than or equal to algebraic multiplicity. That was eigenvalues and eigenvectors. That's it for now.